The next topic in Chapter 4, Section 4.5, is integral substitution. Now let's say we are faced with an integral, like we've got right here. And it's kind of like, I'd like to use something called product rule with the integrals, but there is no such thing. How am I going to find the integral of this? In Section 4.4, we said, hey, if you can simplify it, let's do that before we take the integral, but we really cannot distribute inside a square root or any kind of a radical sign. So that's no good. You have to come up with a different method, and that different method is known as integral substitution. And this is used finding the integral or the antiderivative of a product, where one factor is sort of the derivative of another factor. Now, since we saw this last year, this is somewhat of a review, but a review that's pretty necessary, especially this whole term sort of. One factor is sort of the derivative of another factor. It's not exactly the derivative of the other factor. We got to make it the derivative. Okay. So what we do here is we're faced with this integral right here. We recognize that one part of this is sort of the derivative of another part. And if we notice that, we're going to use integral substitution. Now, the founders of integral substitution used the variable u. Not sure why, but they did. They said, okay, we're going to transform this from an integral that involves x's. We're going to substitute, and we're going to have an integral that involves u's. There will no longer be any x's. And u is going to be 1 plus x cubed. Because if I take the derivative of that, if I find du dx, the derivative of u using the variable x, I would get 3x squared. And then multiplying each side by dx, I would get that du is equal to 3x dx. And now I can use a substitution. Here's my new integral. Now the 3x squared dx, there's a 3x squared times a dx. It's going to get replaced or substituted with a du, and the du, the dx, the d whatever, always written at the end of the integral. This has got to be replaced. Remember, our new integral cannot contain any x's. I'm going to replace that with square root of u, or u to the 1/2. So there's our new integral. And now I'm going to take the antiderivative of that. And the antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2 or times 2/3 plus c. Now you'll notice that this original integral here, this original integral was indefinite. And in an indefinite integral, what you need to do is you need to substitute the x's back in for the u's. Okay, I'm saying that we started with x's. The x's are the starters in our game. And the u is the substitute. But in an indefinite integral, you got to put the starters back in the game. We've got, well, I'll call it 2/3. But instead of writing u, instead of writing this u, which right here, I'm going to write what u is in terms of x's. I've got to put x's back in the game. I've got to take 1 plus x cubed to the 3/2 power plus c. Now, if I have time, I can check and make sure that that's the correct answer. Make sure that's the correct answer. What I would do is I would take the derivative of this. When I take the derivative of this, it's going to be this thing right here. And if that is the case, which in this case it would, and you can take the time to do that by pressing pause if you'd like. If you take the derivative of your answer, should equal this. If so, you've done it right. If not, back to the drawing board. All right, let's take a look at this. We've got a product. We're asked to take the integral of a product. And so I'm suspicious that we'll probably have to use substitution. Does it look as if one portion of this, or one factor of this integral, is sort of the derivative of another part? Well, x squared is sort of the derivative of x cubed plus 1. So I'm going to let u equal x cubed plus 1. The derivative of that, and I'm gonna do the multiply by dx all as one step here. Derivative of that is 3x squared times that dx that came over from having been underneath here. Well, I don't have a 3x squared dx. I sort of have that. I have an x squared dx. How can I turn what I've got here, this 3x squared dx, into exactly what I want? Well, I can turn this into what I want by multiplying by 1/3. 1/3 of a du is 1/3 of 3x squared dx. I got to get exactly what I want here. Exactly what I need to replace so I can do my substitution. The x squared and the dx now gets replaced with a 1/3 of a du. And we know the coefficients come along for the ride. They can be written up front. So I've just replaced or substituted for my x squared dx. Now this. Sine of u. Well, antiderivative, well, 1/3 come along for the ride. Antiderivative of sine u is the opposite of the cosine of u plus c. And realizing that I have to put starters back in the game, this is going to be negative 1/3. Instead of cosine u, I will write cosine x cubed plus 1 plus c. And I do believe that if I took the derivative of this term, I'd end up with that. All right, so there is example 2. All right, now we got an interesting one because this does not appear to be the product of two different things, when in fact it is. We've got a cube root of 7x minus 5. You can think of that as times dx. So if we let u equal 7x minus 5, what is the derivative of that? Well, it would be 7 dx. And as we look at this original integral, we don't have a 7 dx. We just have a plain old dx that needs to be replaced. So to turn a 7 dx into a dx, I guess I'm going to multiply by 1/7 on each side. And 1/7 of a du will replace the dx. So as I write my integral, my dx got replaced by 1/7 of a du. My cube root will be the cube root, or the 1/3 power of 7x minus 5. But remember, you don't have any x's. It's u to the 1/3. And so what we'll end up with here is 1/7 of u to the 4/3 times 3/4 plus c. So I got to do a little multiplication here. 1/7 times 3/4 is 3/28. Instead of u to the 3/4, I'm going to have 7x minus 5 to the 3/4. Oh, to the 4/3. Sorry. Plus c. And I do believe that if I took the derivative of this, I'd get this term over here. Kind of interesting to see. I'm not going to take the time. Why don't you guys check it out and see if I'm right on that. Here again, doesn't look like we've got the product of two functions. But I can think of this as times dx. So I got to get creative here. I've got to get rid of that dx, so maybe I'm going to let u equal 2x. The derivative of u will be equal to 2 dx, which is pretty close to what I want. It's going to be exactly what I want when I multiply by half. Now I have something that can replace or be substituted for the dx. And let's see what this thing turns out to be. Well, let's see. Instead of secant squared 2x, I'm going to have secant squared of u. Instead of a dx, I'm going to have 1/2 of a du. And do you recognize what's the antiderivative of secant squared? And I think we're going to agree that that's going to be tangent. Let's see. But this is an indefinite integral. We got to put the starters back in the game. 1/2 tangent of 2x plus c. I do believe that the derivative of this is going to be that. Integral of sine cubed. Oh boy. Well, I might say, well, all right, I'm going to, and don't write this down because this doesn't work. U is equal to x. Du is equal to 1 dx. Got exactly what I want. I'm going to rewrite this. It is sine cubed of u du. I still don't know what the antiderivative of sine cubed is. So I'm in trouble. So I'm not going to do that. Hopefully you didn't write it. Now I like a good integral that's got sines and cosines in it. How about if I rewrite this, and this is why I got to show you this as an example. How about if I rewrite this as sine squared x times sine x dx. Now that's sine cubed. Well, why do you do that? Well, because I know that sine squared plus cosine squared is equal to 1. And so sine squared is equal to 1 minus cosine squared. I can rewrite this as 1 minus cosine squared. Now, what's the derivative of what? Well, this one's kind of tough. You might say, well, the derivative of sine is cosine. Derivative of cosine is sort of like sine. I could go either way with this. Well, there's one way that makes more sense than others. Again, that's why I'm showing you this one. I'm going to let u equal cosine x. And that way, du, derivative of cosine x is negative sine x dx, which isn't exactly what I have. I have sine x dx. So if I just take the opposite of each side, I've got the opposite of du equals sine x dx, and that's exactly what I'd like to get rid of. I'm going to rewrite this integral as 1 minus, but instead of cosine squared, since cosine is the same thing as u, let's say 1 minus u squared. Instead of sine x dx, sine x dx has the same value and therefore can be substituted by the opposite of du. Now let's take the antiderivative. Opposite sign, u are a coefficient. The antiderivative of 1 is u, because the variable we're using here is u. Minus antiderivative of u squared, u cubed over 3. Plus c. And so my final answer, putting the starters back in the game, is the opposite of, now instead of a u, I'm going to write cosine of x. I'm taking the opposite of this subtraction. So I'm going to say plus u cubed, or cosine cubed, over 3 plus c. And I do believe if you take the derivative of this, you would indeed get sine cubed of x. Now that's the final slide, but I want to show you one other thing. Let me go back here. Maybe to this guy here. And I want to show you this one. I'm going to add a slide. The integral of 3x squared times the cube root of 1 plus x cubed dx. What if this were a definite integral? What if this integral went from, let's say, 0 to 0 to 1. Let's just do 0 to 1. Okay. Now, the fact that it's a definite integral really doesn't change anything. We would go through the u equals 1 plus x cubed. We would say du equals 3x squared dx. And we would rewrite the integral. And the 3x squared dx would be replaced or substituted by du. The 1 plus x cubed, the 1 plus x cubed would be replaced with a u. Let me just go back here. That was square root, sorry about that. It wasn't cube root. It was square root. Okay, so this is the 1 plus x cubed is replaced with u to the 1/2. But I no longer, because I changed my variable from x to u, remember that these things up here, these things right here are x values. When I rewrite my integral, I need these to be u values. Now, if x is a 1, what have you got here? 1 plus 1 cubed, that's a 2. If x was a 0, what is the resulting u value? Well, 1 plus 0 squared. So when you change variables, you have to change your limits. If you have a definite integral, the starters in the definite integral do not go back in the mean. When I take the antiderivative, I'm going to get u to the 3/2 times 2/3. I'm going to evaluate that at my new values of u. So I'm going to drop my 2 in here. And I'm going to get 2/3 times 2 to the 3/2. I have no idea what that is. Minus 1 in here. 2/3 times 1 to the 3/2. Now, what is 1 to the 3/2? It's just 1. And 2/3 times 1 is just 2/3. And this is what I would end up with as my final answer. No plus c, because this was a definite integral. Definite integral, you're doing the exact same thing, but you have to change your upper and lower limit to your new variable. And don't put the starters back in the game. Evaluate your antiderivative at these new upper and lower limits. All right, assignment time.